And denote this mass by m naught. Okay. Then 2, you fill the RD bottle with the liquid. With the liquid. Okay. So you fill it with the liquid and way to get the mass of liquid, or let me use the bottle plus the liquid. So of course you use the electronic balance to determine this weight and denote that by M1. Okay, so now we have the mass of the empty bottle, we have the mass of the bottle plus the liquid whose density is to be determined. All right. Therefore, with these two, you can easily determine or calculate the mass of liquid. And the mass of liquid become M1 minus M0. Please, are we following? The third procedure is that pour out the liquid from the IV bottle. Okay, clean it and ensure that the bottle, both within and outside, is well dried. So yeah, hello.
The board is blue. What you're writing is very blue.
Come again.
What you're writing is blue.
I think it's a network. Please, is it better? Can you see now?
It's okay.
All right. So thoroughly dry. White, okay, white to dry the RD bottle, both in and around with a dry, clean cloth. So after pouring out the liquid, you wipe out in and around the RD bottle with a clean cloth, just to ensure that there is no residue of the liquid left, especially inside the RD bottle. Then you refill the bottle with water. Okay, you refill the bottle after cleaning the bottle both in and out. You refill it with the with water, and then denote this mass by M2. Okay, you refill the bottle with water and then weigh the bottle plus water. Okay, let's denote this mass by M2. How do we calculate for the mass of the water? How do we calculate for the mass of the water? Yes. Bushra, how do we calculate for the mass of the water? Please, let's hurry up. How do we calculate for the mass of the water?
Wikipedia. Please, you
Hello.
said we are naming the mass of the bottle plus the water as M2.
Exactly. So how do we determine the mass of the water in the bottle? Okay, while Bushra is thinking about the question, let Akushia, okay, Akushia come in.
M2 minus M0.
So Bushra, the mass of the bottle plus the water is M2. Okay, the mass of the empty bottle, RD bottle, is M0. So subtracting M0 from M2 would give you the mass of the water. Are you okay? Which are you okay?
Yes, please.
All right. Then we want the density of it. Relative density. The relative density. Here, what are we doing? We are comparing the mass of the liquid whose density is to be determined by the mass of equal volume of water. So RD, which is relative density, is equal to the weight of substance. And a substance here is a liquid, right? Weight of substance divided by the weight of equal volume of water. That is relative density. Weight of substance divided by the weight of equal volume of water. But because in determining the RD, or the weight of the substance, and then the weight of water, we are considering an equal volume of the liquid and then of the water, the volume would cancel out. What is then weight? Weight is mass times gravity. So in our case, we have mass of liquid times gravity divided by the mass of water times gravity. But because gravity will cancel out, this relation for ID, okay, will be left with mass of liquid divided by mass of equal volume of water. Equal volume of water. We've calculated for the mass of the liquid. The mass of the liquid is M1 minus M0. So M1 minus M0 divided by the mass of equal volume of water, which is also M2 minus M0. By considering this ratio, we can determine the relative density of the liquid. By considering this ratio, we have determined the relative density of the liquid. And what is relative density? Comparing the density of a substance to the density of equal volume of water, or the weight of a substance to the weight of equal volume of water, or mass of substance divided by the mass of equal volume of water. Okay, so when you have the relative density of the substance, you automatically have the density of the substance. Please, are we okay? Class, are we okay?
No, please. No, please.
By determining the relative density of the substance or of the liquid, we automatically have the density of the substance as well. So let's use values. Let's use values. Let's consider the mass of the empty bottle to be 20 grams. Okay. Then when we measured the mass of the liquid and the empty bottle, we had 35 grams. Then it means that the mass of the liquid is 35 minus 20, giving us 15 grams. Now, after emptying the liquid, refilling it, drying it, and then refilling it with water, when it is reweighed, we got mass of the bottle plus the mass of the water to be 28 grams. Therefore, the mass of the water is equal to 28 minus 20, giving us 8 grams for the mass of the water. Therefore, the relative density, which is mass of liquid divided by mass of equal volume of water, would be equal to M1 minus M0, we got 15. Divided by M2 minus M0, we got 8. Okay, what is 15 over 8?
1.875 grams.
1.875. So approximately 1.88. Relative density has no unit because either we are comparing the density of a substance to the density of equal volume of water, or the mass of a substance to the mass of equal volume of water, or weight. So the units will cancel out. Okay, so the relative density of the substance is equal to 1.88. Relative density and then density numerically have the same value. Let's turn our attention to the other side of the board. I want to adjust the screen. We are defining RD to be equal to either density of a substance divided by density of equal volume of water. Okay, we calculated and then got the RD to be 1.88. So RD is equal to 1.88. Now, it implies that the density of the substance, which is liquid here, would be equal to, so we have 1.88 is equal to this divided by the density of water is equal to 1 gram per cm cube. Therefore, it means that the density of the substance, which is the liquid, will be equal to 1.88 times 1 gram per centimeter cube. So this becomes the density of the substance we were measuring in the relative density bottle. So the moment you calculate to get the RD, the relative density of the liquid, you have the density, the relative density of the substance. You automatically have the density of the substance. Please, are we okay? Are we fine?
Yes, please.
Okay, so I have given you 3 formula for determining relative density. The first one is the RD is equal to density of substance divided by the density of equal volume of water. Equal volume of water. What is density? Density is mass over volume. So the numerator has density of the mass of the substance divided by volume of the substance. Then divided by the denominator also has density of equal volume of water. So it means mass of water, mass of equal volume of water divided by the volume of water. So the numerator, mass of substance divided by volume of substance, caters for density of substance. Then the denominator, mass of water divided by volume of equal volume of also caters for density of water. Okay, but because we are choosing equal volume, we use the relative density bottle. And don't forget, we fill the substance, okay? We fill the bottle with the substance. When we finish, we poured the substance out, cleaned it, and then poured in the water. So we are using the same volume of the relative density bottle. So volume of substance cancels out with the volume of water because we are using the same volume. So in fact, RD, relative density, simply becomes mass of substance per mass of equal volume of water. Okay. That is how come the definition for relative density is density of substance over density of equal volume of water. But we are breaking it down to mass because the volume would cancel out, just as in the case of the weight, gravity would also cancel out. And in each of the formula, we'll be left with mass, mass, mass throughout. Please, are we okay?
Yes, please.
So that is how to determine the density. The moment you calculate for the relative density of the substance, you have the density, but this only works for density of gram per centimeter cube. It doesn't work for kilogram per meter cube. Okay, so numerically, relative density and density have the same value. Okay, have the same value, but it only works for a density in gram per centimeter cube, not kilogram per meter cube. All right, so that is how to use the RD bottle to determine the density of substances. Agosia.
So please, does it mean even if it's 2 grams per meter cube, you still get the same value for relative density and the density of the liquid?
Yes, yes. The moment, as I said, the moment you determine the relative density of the substance, you have the density of the substance, but this must be in gram per centimeter cube. So if the relative density is 4, then the density of the substance is 4 grams per centimeter cube.
Yes, please.
Gloria.
Mr. Ida, please, the relative density, does it have any specific units that is measured in?
No, RD has no unit because whether the formula is density of substance over density, they will cancel out. If it's about masses, they will also cancel out. If it's about weight, they will equally cancel out. So RD has no unit, but the density has a unit. Okay. Akusha, are you okay? I said Akusha, Gloria.
Yes, please.
All right. Please, have you exhausted your questions? So we can move on. Xavier. Hello, Xavier. Okay. All right. So let's look at Archimedes' principle. As I said earlier, the main topic is fluid mechanics. Fluid mechanics. And the main topic we'll look at, instead of calling it Archimedes principle, let me use buoyancy. Then we'll look at flotation. Flotation. So let's begin with buoyancy. Say it after me, buoyancy. Maybe it's a new word on your list. So buoyancy. Buoyancy.
Buoyancy.
Exactly. The word alone is buoyant. What is buoyancy? Buoyancy simply means that it is the tendency of a body to stay afloat. The tendency of a body to stay afloat in fluids. Okay, so buoyancy is the tendency of a body or an object to stay afloat in fluids. What is fluid? In physics, when we talk about fluid, we are referring to liquids, anything liquid, and gaseous.
Please, is it to stay afloat or afloat?
Afloat in fluids, either liquids, either in liquids or in gases. Okay, so that is the meaning of buoyancy. So ships floating in water. Okay, there's an application of buoyancy. Aeroplanes in air, buoyancy. Okay, so the tendency of a body to stay afloat in fluids, okay, is what we are describing as buoyancy, the major term as buoyancy. Okay, now when objects float in gaseous or liquid medium, there is always a force, a contact force on the body. In reality, the object could stay afloat because of that contact force acting on the body within the fluid medium. Okay, and the contact force which keeps an object, okay, which keeps an object within a fluid medium afloat is what we term as the upthrust or buoyant force. Buoyant force. I'll give you a practical situation. You have all experienced it before, but because your attentions are not drawn to it, you think it's an alien thing. But we have all experienced this force before. So I said the upward force or upthrust or buoyant force within fluids that keeps objects floating. So that upward force, buoyant force, or the upthrust is the force within the fluid that keeps objects floating. A practical experience. If you have, I don't know if you have tried pushing a balloon or a ball within a bucket or barrel of water before, or if you are swimming in a pool, okay, and look at the ball, okay. I don't know if even the live that tube, okay. I don't know if you have tried pushing it within water before, and if you have, what was the experience? Yes, can somebody share with us? Okay, Apia, share your experience with us. Apia, go ahead. Share your experience with us.
Thank you for the opportunity.
Yeah.
Thank you for the opportunity.
Okay, go ahead. Apia, we are listening. Oh, network.
Pause this way back up.
Apia, come again. So, Apia.
Water.
All right. Any other observations? If you have experienced how it feels like pushing a ball within a bucket of water or a barrel of water, or when you are swimming in a pool, okay, what was the feeling like? You always experience an opposing force against you. So you try to exert a force on the ball or in the or on the balloon, and there's always an opposing force opposite to you. The moment as you do so, the moment you take or you take the force off the ball, it pops up. Okay, always as if there is something within the water medium which tries to push back the balloon. If you have also tried carrying a friend in water medium when you are swimming and you try to carry a friend, there is also this buoyant force in play. You see, carrying somebody in fluid, especially in water, is always easier than doing so on land. I'm sure you have experienced that before. If you have, show your hand. If you have tried carrying a friend in water when during swimming in a pool or water or sea, okay. If you tried carrying a friend, and how was the feeling like? You see, it is always easier carrying something in water than when you do so on land. And the feeling is that the person feels light. So okay, the person always feels light, okay, carrying one in water than on land. And the reason has to do with upthrust. Upthrust is the upward force that exists in fluids, but the upward force is greater in water or in liquids than in gases. And this is because of the density of water. You see, the density of water is far greater than the density of gases. And because of this varying density, that is why the upthrust or upward force is greater in water than in gases. Density of water, for instance, is 1.0 gram per cm cube. Okay, density of water is 1.0 gram per cm cube. Density of air is 0.0012 gram per cm cube. Okay, density of nitrogen, which is one of the components of air. Nitrogen is this 0.00125 gram As for density of hydrogen and then helium, very, very, very small. Hydrogen has a density of,
Mr. Dia,
hello,
please, the part of the board where you're writing, the
you
light
can
has
see.
fallen there, therefore it's not clear.
What about this? Is it better?
Okay, now it's manageable. Thank you very much.
Okay. So look at the density of water, 1, and that of air, 0.001, so small. You look at that of hydrogen. Hydrogen is one of the lighter gases, 0.0009, and that of helium, 0.00018. Okay, so if this is the density of water, and these are the density of gases, then it is obvious that upthrust will be greater in water than in all the gases listed. Okay, go ahead.
Go ahead.
Okay, I'm listening.
Density of air is
Okay, I'm
0.
listening.
Density of air is 0.012, but isn't air a mixture of gases?
Yes, air is a mixture of gases. Okay, meaning if you take a single one out, you need to have a density different from the general one. Is that okay? That is why the density of air compared to the density of nitrogen varies slightly. Okay, yes, air is a mixture of gas. Are you okay?
Yes.
All right. So that is it with upthrust or upward force. Now let's look at Archimedes' principle. I said upthrust is a contact force. All contact forces, okay, are experienced when the body or the object is within a certain medium. So upthrust is a contact force. The object experiences it when it is within fluid, anything gas, gaseous, or liquid. Then frictional force is another contact force. Okay, frictional force always opposes the relative motion between two bodies. But we also have what we call field forces. An example of field force is gravitational force or gravity. Once you find yourself within the region, you experience it. Okay, magnetic force is another. Okay, so contact forces, we are talking about upthrust or upward force or buoyant force and friction. Archimedes' principle. Archimedes was one of the Greek scientists, okay, during the classical era. In the olden days, one of the renowned, he was, at least, in fact, one in all, he was an engineer, scientist, and a mathematician. He one day was tasked to solve a problem, okay, a problem of the then king in Greece. And what was the problem? The king then gave a certain quantity of gold to a goldsmith to design a very beautiful crown for him, gold or golden crown. to a goldsmith. Then the king realized that no, what the goldsmith actually brought compared to the quantity of gold given to the goldsmith, he saw that there is some mischievous act somewhere, because he could see that yes, the quantity of gold given isn't okay in proportion with what the goldsmith actually presented. But the king had no clue to draw a conclusion as to whether part of it was stolen or otherwise. Then Archimedes was as I said, one in many. So whoever was confronted with a problem goes to see Archimedes for advice. And so the king invited Archimedes and then narrated a story to him. In fact, it was a burden for Archimedes himself, because it was his, maiden encounter of that particular challenge. And so he asked for some time to think through the problem, and then one day they say, because I wasn't there, Archimedes was bathing in a tomb, or what is now known as a jacuzzi type of bath, filled with water to the brim. Archimedes entered into it and then saw that part of the water it was displayed. Okay, then that act drew his attention to solving the king's problem, and so he refilled and then went into it again, and then he had some overflow of water. Then he was figuring out what was responsible for this overflow. Then came to the realization that there was an overflow because what was displayed was equal to his body volume, connected to the experiment you just described. That you want to determine the volume of an irregular object, you tie it to you tie the object to a thread, lower it gently into a water in a beaker. You denote the initial volume, then denote the final volume. You subtract. So it's the same thing. When the body is completely immersed in the water, okay, the difference in the initial and the final volume would certainly give you the volume of the object immersed in the water. So Archimedes realized that the overflown water is equal to his body volume. And so it gave him an idea that he could use what he just observed to, solve the king's problem. And out of excitement, they say Archimedes went naked, shouting "Eureka, Eureka" on the streets of the then Sicily, shouting "Eureka," meaning "I found it." Then tomorrow he went to see the king. The king, bring the crown. Then he connected this simple experiment that, give me the quantity of gold given to the goldsmith, bring your crown as well. If he claims it is the same quantity of gold that is used in the doing or manufacturing whatever, then they should